next one's a house with 896 square feet, and so on and so forth. Okay, so if I call samp1, all I'm doing is I'm going into this list of 2,930 numbers, and I'm saying draw out 50 of them. Okay, and it doesn't seem like it did much, but here they are right here. Samp1 is right there, and I can ask what is in samp1, and we see 50 numbers listed in sample 1. And these are just 50 houses randomly selected from that listing of area. Okay? And one of the questions says, describe the distribution of the sample. Okay, so if we wanted to create a histogram of the sample, sample 1, it looks like this. Let's add breaks. I don't know if that's gonna help. Okay, it looks a little odd, and that's just because there's only 50 numbers. Okay, and so we see it is still right skewed with the bulk between 1,000 and 2,000, but we just don't have as much of a spread as we did before when we looked at the entire thing for area. Okay, so this is everything for area. This is it for sample 1. Okay, and if I drew a different sample and I created a new histogram, so my histogram looks a little different. Okay, so this is I called the command sample area 50, so it drew another 50 random square footage areas. Okay, so it just has a few questions that it asks about that, and it asks, what is the mean of this? All right, so here you're going to do kind of the sampling distribution thing that I did before. So it asks, what's the mean? This sample is 1,527.66. If I took another sample and asked for the mean of this, I get a different value for the mean of the sample. Okay, and so here it says, run this code. Okay, and so basically just retype this code. And the key here is that this is when it says sample means 50, what it's talking to. So the name of the variable doesn't matter, okay? But we've called this one sample means 50 because when we take a sample, we're taking a sample of size 50. We're taking 50 randomly selected houses as our sample, and we're calculating the mean of that sample. And we're storing it in sample means 50, okay? And so this is the sample size. That's why we're calling 50. This is 5,000. We're taking 5,000 samples of 50. Okay. I think when I did my demo last week, I did like 100,000 or just a really large number. So you can increase this number to 10,000, 50,000, 100,000, whatever you want. It's going to cause your computer to take a little bit longer. But most computers these days are very fast and can run through 5,000 or 10,000 or 100,000 samples very quickly. Okay, so here we're taking 5,000 samples of size 50. Okay, and then asks, would you expect the distribution to change if we collected 50,000 samples? What do you think the answer is? 50,000 samples of size 50 versus 5,000 samples of size 50. What would happen? Do we see a bigger spread, smaller spreads, about the same spread? So when we take 50,000 versus 5,000, the amount of spread shouldn't change too much. Okay? What we're doing here is we're just doing the same thing over and over again. Okay? So it'd be like I tell you, flip a coin 50 times. And then do that 100 times. Okay, so you're flipping a coin 50 times and you're doing it 100 times. At the end of each 50 times, I want you to write how many times you saw heads. Okay, and then you do that 100 times. And then I say, okay, good job, you did it 100 times. I want you to do it 1,000 times instead of 100. Every time you're flipping the coin 50 times, and write down how many times you see heads. Do you expect there to be a huge difference between your 100 versus the 1,000? No, not really. You would expect your 1,000 just to be kind of like multiples of that 100 that you've done, okay? And so that's essentially what we're doing here, what it's asking here. Is it going to make a huge difference to do 50,000 versus 5,000? Probably not a huge difference, okay? It might fill out the distribution a little bit more. So in 5,000 samples, you might see some irregularities just from the random nature of sampling. And after 50,000, it will probably smooth out any irregularities that you might see. Okay. And if you've never seen a loop before, it talks about how a loop works. Okay, so it's just saying, so you don't have to do this. Don't copy this part. Okay, this is just explaining what's happening when you run the loop. Okay, and then it says do sample means of 10 or 100. Okay, so here it's just asking take samples of size 10, take samples of size 100, and it's asking to build up histograms based on samples of size 10, samples of size 50, samples of size 100. Okay, so we kind of did this in class last week when we were talking about sampling distributions, and here you're just kind of doing it yourself. Is that okay? And then it has a few more questions, except instead of dealing with the area of the house, you're going to be dealing with the price of the house. Okay. Skip the last one where it says what concepts from the textbook are covered in this lab. We're not using the textbook related to this lab, but it's similar enough. Okay. And then here, the second part of the lab, lab 4B, is deals with confidence intervals. Okay, so same type of stuff. You're gonna this part, the beginning part is the same. It's just loading the data, and now instead of what we're doing is, I don't know why they call this population. Oh, I know. Okay, so here the population represents the list of all 2,390 houses. Okay, so the population, what we used to call area is now just renamed population. That's the listing of all 2,390 houses. Okay, and then you're taking a sample of size 60. Okay, and then you're taking the mean of that sample. Okay, so far it's all the same, but we're not building up a sampling distribution. We're dealing with a confidence interval. Okay. All right, and so we're coming up with a formula for the upper and lower bounds of the confidence interval. Okay. And so here we are just using the numbers 1.96. Technically, this is not 100% correct, okay? Because we should be compensating using the t-distribution. But for the purposes of the lab, 1.96 is mostly sufficient for this part, okay? And you're going to do this, okay, and it talks about, so you calculate the mean of all, so here we ask the mean of the population, and that is, because we actually have all 2,390 houses and their square footage area, we can actually get the population mean. We add up all 2,390 values, divide by 2,390, we can get the actual mean there, okay. And so what you're going to do here, okay, is you are taking we're going to create a whole bunch of confidence intervals. Okay, so this is doing it 50 times, and each time you're taking a random sample of size 60. Okay, so in the previous part, you're initializing these things called sample mean and sample standard deviation. And we're going to take, and we're saying the sample size is 60. So every time we run through the loop, we're taking a sample of size 60, we're calculating the mean of those 60 numbers and the standard deviation of those 60 numbers, and we're storing them somewhere. Okay? So we're not creating confidence intervals in this step. Okay? We're storing all of the samples, or I'm sorry, we're storing all of the means and the standard deviations of all the different samples that we're taking. And we're taking 50 samples, each of size 60. Okay? And then using the rules for finding the lower and upper bounds, we're going to find the lower and upper bounds of the confidence intervals for each of the 50. Okay? And this is where the vector notation of R comes in really handy. Okay? Because samp underscore mean is not a single value, it's 50 sample means. Okay? And samp's standard deviation is not a single value, but it's 50 different standard deviations, one for each of the samples that we took in the previous part. Right? Because this loop, we're taking 50 different samples, and we're recording each of those sample means and each of those standard deviations in this vector right here. Okay? So we can apply a formula to all 50 numbers all at once. So that's a nice handy feature, or not feature, but just one of the good parts of R. Okay? And this creates confidence intervals for each one. Okay? And so if we plot these, then we will see a whole bunch of these things. Let me see if I can. Okay. Well, I hope at least my explanation will get you prepared for when you work through the lab yourself. Okay. Or I don't know if this leaves you entirely confused, but. So you're just dealing with the Iowa data set with housing data. And in the first part, you're basically building up sampling distributions similar to what I did last week. And then this time, for the second part, you're making confidence intervals. Okay, and you're just taking a sample and then generating upper and lower bounds based on the formula for a confidence interval. And then you're going to see what those boundaries look like versus the actual population. So here we know the population, and we can see if our confidence interval captures the true population mean or not. Okay? But anyway, don't worry about that too much until after the midterm. And with that, I'd say good luck as you guys study this week.